For the generalization, we want to be able to find global extrema of any function on any interval if those extrema, those global maxes or global mins exist. It's possible that they don't if we have just a general function on a general type of interval, but if they exist, we want to know what they are. And so what we need to do is we've got two types of important places. We've got plug-in values. So I'll say plug in, and we've got limits. Basically, it amounts to points that are there and points that are not there. And so for the points that are there, what we need is to take a look at critical points that are in the interval. So we've got the critical points that are in the interval. Any critical points that are outside, we don't care about. But the critical points that are in the interval are plug-in values. They are important points. They are there. We need to know what's happening. The other thing that we need to look at is any endpoints that are included in the interval. So any of the endpoints that come with a bracket, not a parenthesis, so endpoints that are included. Those values are in the interval. They are plug-in values. We want to see what's happening. But then these limit values, the other important types of places, would be the places that aren't there, but we need to know what's happening nearby. We need to know what's happening at or near. We really are saying near when we're talking about limits, so that we can compare those values for the function nearby to the values that we have that are actually there, that are the plug-in values. So the limit values are coming from discontinuities. And not just any old discontinuities for any function, but rather the discontinuities that are in the interval. If the function has a discontinuity but it's not in the interval, we don't care. Just like if it had a critical point but it's not in the interval, again, we don't care. The one thing that we have to be careful with, though, with the discontinuities that are in the interval, we need to look at both sides. It's possible that the function is doing different things from the left and from the right. Perhaps if we had a vertical asymptote, one could be going to positive infinity and the other side being going to negative infinity. So we need to be able to look at both sides of any sort of discontinuity that we have. And the other thing that we need to do is we need to look at endpoints that are not included. So endpoints not included in the interval. And for those endpoints, those would be the ones that would be coming with a parentheses. They're endpoints that are missing. We're going to that but not hitting it completely. And so we've got endpoints that are not included in the interval. We need to make sure we look at it. And what we're going to be doing is we're going to be looking at the side coming from the inside of the interval. So look at the side from inside the interval. So for instance, if it's the left endpoint that's missing, we're going to be looking at the limit coming from the right because that's the part of the interval that we would be inside moving towards the edge, which would be the endpoint that's not included. And so what we get for our conclusions then, once we have all of these things evaluated, some of them evaluated because they're function values coming from plug-in values, and some evaluated because they're limit values coming from limits that we've taken. So we will have all of that data, and we'll still be looking for the biggest and the smallest, but the problem here, or the thing to remember here, I'll say, is if the biggest or smallest comes from a limit, the max or min isn't there. But if the biggest or smallest comes from a plug-in value, that would be a max or a min that we have. And so we're going to go through this sort of scenario with an example. In this example here, we're looking for any global extrema that we might have for the function on the interval. And so this particular function actually happens to be, it's a polynomial, so it's continuous. It has no discontinuities. And so we want to note that first. So discontinuities. We'll say none, because that's one of the limit things that we had to take. So we have no discontinuity, so we're not going to have anything that goes into limits from discontinuities. The other thing we need to be able to compute would be critical points. And so to get critical points, we need to take the derivative. So we've got the derivative of a polynomial here. So it would be 2 times 3 is 6x squared. Minus 3 times 2 would be 6x, and then minus 12. And so we want to go ahead and get this in a nice factored form. We've got a greatest common factor of 6 on all of the coefficients, so that'll help us actually factor it nicely to begin with. Pulling out the greatest common factor of 6 leaves us with a leading coefficient inside the parentheses being 1, which means we can factor that more simply. We're looking for two numbers that multiply to give us -2, that add to give us -1, and that would be a +1 and a -2. And so those two numbers give us the factorization right off the bat because of the leading coefficient being 1. Okay, so we've got this factorization now, and so to get critical points, we're looking where is f prime undefined and where is it equal to 0. Well, it's equal to 0. This factor 6 gives us nothing because there's no x there. 6 never is equal to 0. But the x plus 1 is equal to 0 at x equals -1, and the x minus 2 is equal to 0 at x equals 2. And then, like we mentioned before, f prime undefined is never. So not only do we need the critical points, we need to make sure we're only looking at those that are in the interval. And so we actually have, let's see, the interval there is -2. Oh, I made a copy error here. Let me fix this interval. The interval is -2 to +1. Sorry, that was a copy error for the example. -2 to +1 is given, not a -1. So given that correct interval, we have the x equals -1 is in the interval, but the x equals 2 is not. So not in the interval. Okay? So the one critical point we have is -1. And so at this point, once we have found discontinuities and we have found critical points, we're ready to start in with our plugins and our limits. So plug in first. Plug in, we're supposed to include any critical points that are in the interval. So we saw that -1 is in the interval. And so we're going to plug that into our original function because we're talking about what's happening to the original function, not the derivative. We know that plugging a critical point into the derivative gives it 0 or undefined. That's not helpful. Here we're just trying to plug in and see where the function's going. So we plug in the -1 to our function. So we're looking at the -1 cubed is going to be -1. So we've got a 2 times -1, which would be -2. And then the -1 squared would be +1, so it's just the -3 then. And then -12 times -1 would be the +12. So we've got -2 minus 3 is -5, plus 12 would be 7. And that's our plug-in value. We would also include as plug-in values any endpoints that are included, but see, this is a completely open interval. Neither endpoint is included, so that's the only plug-in value we have. So now we're ready to go to limits. So for limits, we would be taking any discontinuities that are in the interval, but this function doesn't have any discontinuities at all, definitely not any in the interval. And so we don't have to look to both the left and right of any discontinuities because we have no discontinuities. But what we do have to do is we have to look at the endpoints. And so we've got the limit as x goes to -2. Since it's the left-hand endpoint, we need to be coming in from the right because that's where the interval is of the function. And being able to take either left or right side limits for a function that's continuous amounts to just plugging in that value. So what we're really doing still is a plug-in sort of thing, but we're understanding it as a limit still. So we've got 2 times negative 2 to the third minus 3 times negative 2 squared minus 12 times negative 2. And you can take my word for it. And this value here would be a negative 4 overall. Then we've also got to look at the right-hand limit, the right endpoint. And that right endpoint is x approaching 1, but since it's the right endpoint, we're approaching it from the left because that's where the interval is. So we are looking at the limit as x goes to 1 from the left, which amounts to plugging in 1 to our original function to take that limit. So when we plug in 1, we get, it would just be the 2 minus 3, which is negative 1, minus 12, which would be negative 13. So now that we have all of the data, we've got 3 numbers to compare, 7, negative 4, and negative 13. And I see that 7 is my biggest, and negative 13 is my smallest. So it's not as simple as just saying, oh, the biggest is your max, the smallest is your min, because you have to pay attention to whether each one of those came from a plug-in value or from a limit. If it's a plug-in value, the point's there. If it's a limit, the point's not there. And so the biggest did come from a plug-in value. So we have global max, because that's where the biggest is, of 7 at x equals negative 1. And the smallest came from a limit value, and so then our conclusion there is no global min. So it's very similar to the extreme value theorem. The only difference is we have to look for discontinuities, and then we've got to pay attention to values that are plug-in values because points are there, and values that are limit values because the points are missing. Especially when you have discontinuities, you've got to make sure you've got both sides that you assess, both from the left and the right of the discontinuity if it's in the interval. But it still amounts to more or less just plugging in, taking limits, and then looking for biggest and smallest. If the biggest or smallest is in a plug-in, it is a global max or min. If it comes from a limit, it means that particular max or min is missing.